Here we go back again, now this time with the Croatian Olympiad in informatics, in competitive informatics. So this is pretty well known here Olympiad in the Balkans. It starts in 17 seconds. This is round 2 out of 5 or 6 rounds. We're going to have probably some five problems, 3 hours to solve them. And yeah, let's here are the statements in English. Just gonna download them. The same file name as the previous Olympiad always. Oh nice, now the logo is changed. 5 tasks, let's go, let's see. What is task 1? One magical night, Patrick and Josip were talking about the number 42 in the beginning of life. Paula was carefully listening to their conversation. The problem of finding the shortest ride interested her so much that she stayed and traveled longer just to listen to the conversation in the tram. At each station, except for the first one, they entered the tram. Unfolded things happened. Said 10 minutes have passed since we entered the tram from station. Why to this station 10 minutes passed? But before Paolo could hear their conclusion about which ride was the shortest, they left the tram. Paolo remembers all the statements, so there are number of tram stations, duration of the ride between station 1 and station this, duration between station Y and station this. It's distinct. Yeah, so we have some graph. Now it's a bit of a not that cool problem, but okay, so we have some queries. For each query we are going to say that, okay, if this is known, if it is Patrick, so if S is Patrick and if it is Patrick, we know that now distance is an integer to this city. Now what we need to output, one line, output 3 numbers, duration of the shortest ride, and the indices starting and ending stations of that ride. So we're going to I'm not sure if this is connected graph or this is like all with all. between station I and I plus 1, y and I plus 1, so between station 1 and 3, 7 minutes. So let's just draw this if I'm not making any mistakes here. Patrick says so there's 3 stations. From the first station to the, so he says, okay, from here to here is 3, from here to here is 5, and from here to here it's 7, right? And then we can conclude that from the second to the third station it took 2 minutes. I believe they are in our line. But here there's like 3 and 5. There's this 2 also, right? Or am I? Oh no, this is not the correct station. This is like this 7, and then from here, yeah, but still, like, this is 2, this is 2. Y smallest indices 2 and 3. 1, 2 and 3, yes. Yes, okay, so I mean, okay, whatever. Okay, y and time. So essentially it's like this. You have some distances. And then you say distance at I is equal to this. And then distance at I is equal to distance at y plus time. And y is minus, okay, yeah, I will do this. I mean distance plus 1, and then I will do this, and then distance. Yeah, so this, the distance at I is equal distance at I is equal distance y minus 1, and then if this at I minus this I minus 1 is smaller than the smallest base, smallest this I minus this I minus 1, s at x is I minus 1 I mean is x plus 1. Do we need to print out? Yeah, we need to print out the distance as well. I believe this is the solution. Actually, there's no time penalty for this problem, so am I not doing something with the distance? Is distance -1? It's 5. Now this should be 1, 2. What is going on here? Oh. Yeah, this is correct. Okay, now we upload the problem. Upload the problem. While this is compiling, we can just duplicate this and delete this. Gets accepted. Let's go to the next one. We have time. Okay, so what is this? The group stage of the World Cup has ended. The teams are ready for the knockout stage. One of them is Boris, the man who correctly determined the last 4 world champions. Lower the chances of this team because they have a player of Barcelona. Okay, doesn't. The audience suddenly got very quiet, especially if Croatia is going to win. Boris will multiply x and y using his famous method of 4 registers. He has 4 registers. Initially they have values x, y, 0 and 1. The only operation he is allowed to do is summing up 2 registers, possibly the same, and storing the result in one of the registers. Each of the registers have the value at most of the time. Okay, he doesn't want the audience to wait long, so he can make at most 100 of these operations. So summing 2 registers and adding to the third. Right. Help him determine the operations he needs to do, and in which of the registers will be the final result stored. doesn't need to have a minimal number of operations. I'm just not sure what it asks. Need to multiply integers x and y. So we have x and y and 0 and 1, and then we need to sum them up, and actually in order to multiply. Okay, so what you do is you sum up two of them and you put them in a third register, and then, but now because we don't want to, okay, we have one register which is 0, so we can use that to actually make the binary x exponentiation possible. Okay, so it's not that hard problem. Let's say x and y. It's just now we have to think about how to print them. Okay, so how do we do this? We do this by saying we have x, y, 0 and 1. 1 is, we have to have that, but now x and y are going to be, so I will multiply always x. Yes, so like log of, yeah, so I will multiply always x, so like I will do x plus x here, and then I can always do this y times. So I already have this binary. This, I will just say that, okay, the result power is y, while power is actually, no, I will rewrite this. I will rewrite this like this. So yeah, so power is y, and then the result is result times base. Times base is times x. There's no times base. It's like here, if the power is this, we can override the x register, right? The y register. So this is just saying I have this. Can I override this register with the same times 2? Probably I can. Yes, so I can. The base is here, it's times the base. So I will see out first X, first A, B, A, C, C. Okay. And then I can do no. Yeah. C, C, C. And if this contains, if this bit is on, which means that we need to sum one up. We are going to do C, what, and then you say how many registers. Yes, so so we only need like this, like a string, and then in what register do we need to add up? X squared, x plus x squared. It's what actually we need to do x plus x plus x y times, right? And then y actually has to can be divided into these groups of whatever x's we have here. Okay, and then so we need to now flip this, right, to do this register properly. So the first time I'm adding a y, I'm adding x to the y, is from x, from A, C, and I'm adding it in the y register, in the in the B register, right? Or what we can reset the beer. We can, yeah. So this is a trick. We reset the B register, reset the B register, and then we add this up. See, we actually add C to the B register. Actually add AC to the B register, and then we want to push back A. And then we always end up in the B register. Is this correct though? Means CCB, B is reset to 0, A is like a 2 plus 3 plus 3, and then 3, I mean this should be fine. I don't see why not, except like if there is like 1, this should be fine as well. 8CP. It doesn't have to minimize them, so it's wrong answer. Why is wrong answer? Is it always wrong answer? It's even on the first test case it's a wrong answer. Oh, maybe we're overflowing. Yeah, like maybe we are overflowing. Okay, now samples passes, but here is wrong answer. What are we missing here? Is it overflow? Oh, I see 60 operations, but here we use more operations to get this up. I see it's more, it is used more operations than 100. So if like some big number is involved. Yeah, I see. You overflow this number quite quickly. But then you have to, yeah, x times y is 10 to the 19, 10 to the 18 power, so you don't actually overflow. Well, we can swap them. CCB clears the B register, ACB clears the ACB adds 1 to there, and then AA goes +1. So that's 2x, 4x, get the 4x in, and then yeah, I see. I mean, yeah. If x if it will overflow, I had to know if it will overflow, so not to, or should we swap registers? So if I use something like 128 bit number, it's fine. I'm just can they make it overflow again? swap x and y. It overflows this register. So if I can submit again just to see what's going on. Why this shouldn't overflow now? Wait, what? No, C, not C, B. Add to the B. B plus equal A now. This is 8 plus equal A. And this is B equals 0. Like this. How does the sample pass this? Okay, we have the first two clusters, okay. Now we need to just fix how we deal with, we have to be a little bit more efficient because 2 times. Maybe we can just get away with like flipping the clusters. So like solve for, so this like in a solve function. this is not going to be enough as well. Maybe we need to combine it even. We got it. Okay, so when we have this problem down, go to the next one. Geometry problem. Okay, what about some string problem? Let's see for the string problem because it's smaller. On their winding walk, they find a pile of words. Excited by that, they quickly started collecting them. Collected n words and m words. After admiring one move, a player says a word from her pile. The player chooses the word in such a way that the following conditions are met. Word is lexicographically greater than the previous word, and it begins with the same letter as the previous word, or with the first letter of the English alphabet after it. Okay, if the player can't make a move, she loses. Alternate turns. Plays first by saying her lexicographically smallest word. And Zoe play optimally, determine who wins. So you have a graph. Now the trick is how to find can they play, because they play lexicographically greater words always all the time, they cannot play the same words. So in a sense it's like, okay, it's game theory, but it shouldn't be that hard. Okay, so what we know that he will lose. So we know that we have some bipartite graph. And a word. Okay, so if I'm here at this word, I can she can, if she is like on the, I mean, she is on the move, right? She can play, just up that brightness here. She can play a word which is either lexicographically bigger than mine, or it starts, or what it says, it's graphically greater than the previous word. It begins with the same letter as the previous word, or with the first letter. So like, okay, so what we can connect is we can connect these that begins in the same letter. So if this is like A, I can move to these positions here with the same letter and are lexicographically greater than this word, or I can move to a position which has the next letter. Okay, and then I can the next letter is always lexicographically greater than my letter, but I cannot go to, like, if here is B and here C, I cannot just go to C. So I have some, what I need is like some two sec trees somehow to communicate with each other and to query out data with each other. Okay, so let's see how we call this. We, at the end, we're going to lose on some word. If I end up in this word, so how to technically look at this? Okay, if I'm winning, if he or she is winning and I end up in this word, okay, so if here I'm losing at some word, she has to just find in this range a word that is losing. And say, yeah, sure, I'm winning here. But here I am losing. I'm losing if and only if for all of this range is winning. So if the range sum, if the range sum is equal to the length of the range, then it means that I'm losing. Else I'm winning. And we have like two sec trees, and then we can query out both of these sec trees. Okay, so n line contains Leonard's words. The trick now is to find which range has like which range is. Okay, so like this, we make a vector of Leon Zoe. We have two sections. thing to be remembered. Now we have to have 2 pointers and to say that okay. Okay. Two segment trees, and now what we go is we say okay, while L is bigger than 0 and R is bigger than 0, if Leona at L is lexicographically smaller than it means that I'm on the, I can calculate it for this here. So and the trick now here is to find the range. So we need to find the range where, so we need to find a range where we have some string S, and we need to find all compatible strings that I can go to. Okay, and what I need to and where do I look? Where do I look for these strings? So I get the vector look, and I find the first string which has first string which is lexicographically greater than my string. Is this the case? So okay, so lexicographically greater than my string. But if they have the same strings, are mutually distinct, and they're also sorted, Oh, so if they're sorted, I don't need to sort. Okay, so I want to find out where this is. So this is lower bound of this vector. For this string. If it equals look at n, then we just return the result. Okay, now we have found this string, and now we need to find a string which is for the next word. So the next word string is a bit more complicated. The next letter, it's still a lower, it's okay. The result here, that first is it minus begin, and then it's a bit more complicated here. How do I see this? So like I create the next string. If s of 0 is already z, the result will be the result that second will be the end of the look. Because we cannot do anything furthermore. If not, we can find the next letter, find the next string, and see if it's not the case, I will find a string which is smaller than this. If this is the case, we want this string. Actually, we want to go to the end of this, so I want to Maybe we can just binary search this here. If look admit is so I want to change if it is invalid, else is valid. When is not in, when admit is going to be invalid? If this here dot 0 is twice bigger than this, then certainly it's invalid. Now we need to find the range of what string. We need to find the range of string of this string and in the Zoe vector. And this is the other way around. Now I'm just going to see out the ranges. I'm going to see out the length, this and the ranges. To see if our binary search actually works. Here we start with Brazil and then we crash somehow. Or no, we end up in like so we go Brazil and then what we do, we go like -1 on R and then starts with the word avocado and then so it continues her own word, can't make any move. So I mean, technically, yeah, technically it has to be the other way around. So it has to be, we find Brazil for this one, right? And then we go double and then go over. So you need to, like, okay, we find Brazil this one, then we go like this, and then we still have to do while both like this. You still have to do, yeah, the avocado on the end, right? So like, okay, so we say double, there's no here, then we say Brazil, which like goes one to the avocado, but then here on L is actually stuck with 0. Why is it stuck with 0 here? It's because the midpoint here, 0, is greater. So we need to find L, right? So L is valid. L is not actually valid. L is, the only valid thing is the first character. And then R is the size. Okay, so he says 1, 1, which means double is valid character. No, it's not. It's, okay, it's lower bound, but if it and 0 is bigger or equal than S0 plus 2, then it's invalid. Okay, so if the range in fact is invalid, we lose at that point. So if it's not invalid, then we have to we lose in this point. But if it is valid, we can query on the other segment tree and say, okay, I will query like this. So this segment tree, this is a segment tree. I will ask from R to left, range first, range second plus 1. What? Oh, so like, yeah, auto node, or just in some value. And then what we said, if the sum of that range is equal to the length of the range, if this is the case, we are pretty much losing here. So if it is not equal, then I'm going to add to my tree at this position 1 and yeah. So that should be the same here as well. If I will ask for this sec tree, and I will put here. So okay, so this won't change anything here. So the range in this 0, 0 will be one element. Wait, so here at the end, so no, so I'm actually reversed here, right? So I can say this word and then I win only if the sum of the range, if the sum of the range is equal to the sum of the range, I'm losing here, because I can say this word and I win here. But actually, if the sum of the range is otherwise, I can say this word and I practically win here. But the trick now becomes the trick if I have any starts with the lexicographically smallest word, or lexicographically smallest word. So in fact, I just want to ask the tree about 0, 1. If I win or I lose. This is correct and this fails. Where does it fail though? So we have 1, 1. Then we play this. Yes, something fails here. Oh no, it's okay. Like -1, -1, -1, -1. Then we go L. Yes, so if L is not -1, we want to check. Okay, now it seems correct. Just going Let's try to upload it to see if pass some test cases. That's the wrong answer. If I'm here, I definitely win. If there's nothing, if she can do nothing here, so I definitely win. What if R is -1? If R is -1, or because R can become -1, right? New message. R can become -1. I'm not sure what kind of this is a new message. Still fails. Test answer, the rectangle with area 0 are not considered to be rectangles. I'll see this. So what could be wrong? If I have these win and this I say A, I say A says C cannot be set. That's the trick. C cannot be set. Yes, I understand the task. The player chooses the word and said that word is also greater than the previous word and it begins with the same letter as the previous word or with the first letter of the alphabet after the previous word. So you cannot say that. But if he said if there is BB, then Zoe wins because BB is now set to 1 and then okay, so what can be the mistake here? There can be some kind of mistake if there is like Z and what letter is before Z? Y. So like if there's Y is the smallest and then there's Z and then there's Z and then there's ZZ again or something like that, I don't know. Zoe should win, yes, that's correct. What about there is like Z here, ZA, ZB, ZC, ZD, something like that. So I say ZA, ZC. Yes, so they are lexicographically sorted, right? Not to be words only lowercase, mutually distinct, their total length, the name of the winner. So it has to be C. Oh no, let me just for a moment. So the trick here may lie in the binary search. But I don't think so. Like, this is correct. Here we find the range. Say if this is the case, we just put in here. If this is the case, if the sum is equal to the if it's equal to the range, the sum is equal to the range. If r is -1, what happens then? It's still correct. Like, I mean, range r is -1, we do this. Because we're left, or L is not -1. Do this. If it's L is -1, then we go R. And then, okay, and then we ask for the value of the lexicographically smallest Illinois term, right? This is correct. This seems correct. Doesn't have to be the lexicographically smallest. When starting, the word is lexicographically greater than the previous word, and it begins with the same letter as the previous word, or with the first letter of the the trick here is if it is Z, oh, it has to be an upper bound. Because what happens if we have the same letter? That's the problem. What happens if we have the same word? Cannot be the same word. Still not correct. So, okay, what happens if we have the same word? So, like this, and then we have the same word, and then we have like CC. Okay, so like if I have AB, then I still win here. Okay, so now here I don't win. Here I still win. Oh. Yeah, I still win here because he says A B, and then I still win. If I'm B, yeah, he wins. If I'm B, I win because A B B. But then if I say so like I have okay I have A B A C. She has, okay, again, A B A C, no? So I say A, I have to say A. She can say directly AC, and then she wins. Here's edge case. Here's some edge case that doesn't work. So I say AA. It's definitely AA. Then you have to look from here to here, and she wins here, or she loses here, and I see. She loses here, and she wins here. Okay, so this is not correct. This is not correct. The correct idea is if she wins anywhere here, she can say this word and I lose here immediately. But if she loses everywhere here, I can say this word and and I win. So if the sum is greater than 0, if the sum is exactly 0, I win. That's the thing. The sum is exactly 0. Okay, let's try to submit this one. The sum is exactly 0. I then win. Yes, we got it. Okay, yes. Okay, now we are going to interactive problem. No, we're going to try to solve this one here. Okay, so Christmas is coming. There has a big rectangular shape. It is n meters by m. Theo has decided to decorate his terrace in a very strange way. Instead of hanging Christmas lights on the edge of his terrace, he will put them on the floor. There are 2K lights, 2 per each K colors. Okay, so there are K colors. He will put each in some position. Proud of how he decorated the terrace, he decides to make the rest of the day off. But so bored, he started counting nice rectangles. And rectangles nice if for each color, both lamps are either inside or outside the rectangle. This is located and the rectangle is considered to be inside the rectangle. Alright, so N and M go to this, and K goes to this. Okay, so how do we count these rectangles? Okay, so how do we count them? A rectangle is a nice n goes to 150 only, which means that there is one more dimension of n I can use, but how many rectangles are there at the most? 150 times 1000 times 150 times 1000. Okay, so we need to reduce the problem to finding for this point we can iterate all the points, and n only, let's say that this is n and this is m, and like I can iterate through all of these and see how many rectangles. So just fastly query how many rectangles are good in this area here. So like think in the terms of n squared times n complexity times some log factor. How do we query them? Like, how do we query them? Is a problem. We say that we want to we can write brute force for this one pretty easy. For each color, there are at most k colors, right? For each color, I'm going to put plus some integer and minus some other integer. But the problem is no, the problem now there's too much problems with this. Like, you cannot do that. You cannot just do hashings on this. It's too big of a space. How do you quickly say is a rectangle? Even if we brute force, how do you quickly say how many colors are pairs of colors with this? Because there's no real way of saying. So if I have two colors, right? If I have two colors, all this rectangle is valid, and all rectangles which encompasses this rectangle are valid as well. So now the problem becomes, as we say, okay, we have some kind of rectangle, and is this rectangle intersecting some other rectangle that it shouldn't intersect, right? Has to be like, doesn't have to be exact cover, but it has to be some cover. Okay, how do you quickly say what intersections? How do you check this? One thing we can do is jumping, but like it doesn't necessarily work. Like, if I have like rectangles here, I'm looking. Let's say I have this rectangle here. I'm here at the position ij, and this rectangle is with some size. I need to query on this border what is the next rectangle, and then what is the next line, valid line, right? And then, okay, here is this line. Now I need to query, does this line I intersect some other rectangle? And this is hard as well, like querying this line rectangle intersection in of probably one. What I'm thinking, like having like persistency, that like I can jump quickly. But still, this is not a nice problem. Let's see. Let's see this. You're an and not just a regular and obsessed with cruhology. Okay, so that's breadth. The slice of bread can be imagined as a collection of unit cubes. Let the total number of faces of the slice of bread be n. Okay, all units are connected. For any two cubes sharing just one edge, there is another cube that shares a face with both of these cubes. So, okay. Currently you're on some face of some cube and orientated in an unknown way. You know anything about the global structure of the slice. You confidently carry around the marker you stole from high school and leave tiny marks. You can erase the mark as well. You can repeat any number of following operation 2 times. Make a step in the current direction. Oh, this is interactive problem. So like make a step in the current direction, rotate left to right, and if the current face has mark on it, also you can be make one. Let's remove it. Okay. What's the output? Number of holes in the slice of what? The number of holes? Really? I mean, okay, we like if you find like this, then like this is one hole, then like rotate. That's insane. No, this problem is insane. This problem is insane. Let's just solve this here. And we'll leave. Can we get some cases here? Maybe subtasks? There's most one hole in the slice, so like either 0 or either 1. But still. Still. How? How would you... I mean, no. Let's see. How do we quickly say? Oh, we can do union of rectangles due to the fact that like if two rectangles intersect each other, the union has no, not exactly. No. You can have exceptions, yeah, like not exactly. So what else we can do? Okay, colors. Like some matchings? But how do you do this? This is a huge graph. This is a grid graph with like huge number of edges. So wait, how n goes to and m goes to 1,000? So probably they can repeat. Oh. Yeah, now the problem is how do you answer this like really fast? it has to be n squared times n. I don't see how else would you, but I don't either see how. Nice rectangle also can contain no lamps at all, right? Yes. Can contain no lamps at all. Not quickly see. How much time do we have? 1 hour? So it's important. Okay, if this is some point here, it's important that. No, I mean, I don't know what's important. Well, even if we look at this problem another way, like from the perspective of K, from the lamp perspective, you just cannot model it. There has to be some kind of trick here, except for like, because n only goes to 150, like some kind of trees that would for each column remember how many, like for, okay, so we can query. I don't know how to check if it is a nice rectangle very fast. How to properly do that? Because there could be some, like, if you want to check if some area of like nodes, some area of like there's so many points K though. So many points to keep track. Like something to do with this, like it's valid sometimes, like here to this point, let's say it's valid, and then here it becomes invalid for all of these points until we have a match here. But also, how do you know that, like this, for example, or this actually is valid? So it's only after this point, so it's some kind of sec tree. It has to be some kind of segment tree. It has to be some kind of segment tree which is easy to I don't know, like I'm thinking of some kind of persistence, but there are only 100. Yeah. So like if when I add this, so like what about like 2D persistence? So like when I add this k and this k, what I do actually, like it has to be some kind of DP width, because these have to be the same. Yeah, no, because I don't know. What is the smallest samples we can pass on this problem? So the first sample is for each lamp color. So the first sample is just x and y is equal 0. Just count this. Relatively easy. Second example is relatively easy again. So we can do n times m times n times m times k. And we'll pass. M 150 times 150. For the third subtask is like, I don't know, like I don't know actually what to say. For the third subtask is n times m times, like okay, we go n times m times. How do you check this quickly though? How do you check quickly? How do you model this problem is the problem. How do you model it? caching is not supposed to work. What's the invariant? What's the invariant of the rectangle which is equal to the, so what is the invariant? So you have some nice rectangle, right? And you move it somehow, and it still remains nice. What's the invariant? Okay, first thing, like, okay, I'm not saying if they contain the same number, the same points. I'm saying what makes a rectangle not nice. Yes, that's probably the solution of the problem. Count the rectangles that are not nice. Okay, we have all of these rectangles, right? And now the not nice rectangles are only these which contain a point, at least one point, which is both ways. So for each of the points, for each of these here, for each of the line, I can construct some rectangles. Which actually are not nice, right? But these rectangles intersect with some other rectangles. Actually the same with some other rectangles. So inclusion, but exclusion won't work. It's too big. So I mean, we can. It's not fun. Even this case is not fun. How can you check this very quickly? Inclusion that are not nice. I mean, has to be some kind of iteratable segment, some kind of this sweep line solution. So you go like, okay, you go this, and then you go sweep line, and then okay, you find this, and then when you find this, you know, okay, this is let's say valid. How do you go to the next line? Okay, like let's say this is the next line. You go, but this here also intersect. And then you skip here, it also intersects, and then you skip here. So you need to jump over lines which have equal over lines which have but there could be a lot of these lines, right? Actually, when we intersect like one line, we can jump here and then jump to the next line. But in the process of jumping to here, we have encountered some new point here. Now we need to jump to that point here. So it's some kind of convexity. But this convexity actually, so for each of these slots and for each of these n times n, we need to construct this convexity thing. So n times n for each of these, go times m, something pre-compute, something, some jumps, then pre-compute some jumps, no? And then construct some sliding window action. Probably something like that. Just So yeah, so for each of these, so we have int n m k. For each of these n times m, so let's just insert all these. Let's just, I mean, I can't use it here. I don't know how to structuralize the data here, but I have to read it. So what we're gonna do is this. We're gonna say the left coordinate and the right coordinate. So the right coordinate is actually left plus 1. And in this segment here of coordinates, so there's 336, 336, and 7. So in this segment of ranges, I just want to find out which of the k segment actually. Yeah, we will need like a matrix to store this somehow. Okay, but whatever. So we have this n square ranges, right? And then for each range, we need to quickly look to say that in like linear time, walk up the range and say, and like have like a sliding window in a sense of a way, right? So like, it's not really a sliding window. It's not really a sliding window because I can I do something with hashes? Can I quickly say, okay, so I have some range here, some left and R range, and now I have some m rows, which, but some might contain some rectangle like this and can never. Yeah, so like if you contain a rectangle like this, either you are limited like this or you're limited like this. Because nothing in the actually like this, but this is another. So like, okay, we are going to have only this width of the rectangle. Now I just need to say, okay, for this, how many valid other m's there exist? And how do you say this quickly? When I come here, I need to look at the valid imps. I need to like somehow prefix sum that. And the way we can do this is somehow like what should we store the data in, because K is so big. K is so big that should we store there is some convexity involved. Because if I encounter a point, so here I encounter this line, I can still go further, still make this, because if here is the point and here is the point, I still make this. But if I encounter a point, I can only make it till I have seen this point encounter somewhere else. So if I have a set of whatever I have encountered points, I need so like some so something like this. So if I encounter a point, I put all these points in a set that I encounter, right? And I remember how many possible rectangles are below it. Then when I encounter it again somewhere up the stream, and I delete it from the set, I also know the possible rectangles below it. But if I don't encounter it anywhere in this range, I will have far more problems than I can. Can we just solve like a subtask, like this subtask? Okay, so for each of these lines, right? Let's say like this. Okay, so for line 1, what is the number? Check inside this if is valid, this rectangle. I think there will be integer number of rectangles, so like most to the 31. So okay, so how do we check it? We go through, we have to have some kind of matrix. We have to have some kind of a matrix. So we should pass the examples with just iterating over all of these and seeing if they're okay. So like I'm just gonna make a function here which will have like 2 points, x, y, and a and b, and then we're gonna say if, so I'm going to order these in a fashion way that if x is small, if a is smaller than x, I'm going to swap so yeah, so I want to order them by, not by x, I want to order them by y. If b is smaller than y, I'm going to swap x and a and y and b, and then I just have to check if it is inside if x is bigger than equal than x and if y is bigger than equal than y, and x is smaller than equal than a, and y smaller than equal than b. This is for one of the insides. Now this is the other. I will return that inside one XOR. So if inside one is equal to the inside two. So I can go through each of the key points. Say if L at I dot OK, and now we say that okay, so we say L A L B R A, and if it is so, if it's not okay, say okay false, break. If it's okay, answer false. This should work for the sample. It doesn't. Oh, so it's +1 everywhere. As far as I know. Okay, so I mean, I will upload this just for seeing if it will pass some set, and then we'll try to optimize it. To optimize it, we need to, okay, it passes some sets. Cluster 2, right? That's what we wanted to pass, cluster 2. Cluster 1 can be passed easily with just an if statement. Cluster 3 is not that easy. Okay, so how do we optimize this? I need some heavy data structures here. Heavy data structures. Okay, so what we said that, okay, we encounter a point. Until we encounter a point, we go linear. We encounter a point. Until we encounter a point, we just go linearly and I update the prefix, right? Well, what happens when we encounter a point? When we encounter a point here, it happens that until we encounter the next point in this set, absolutely nothing we can do here ending at this point. Absolutely nothing we can do. So we can just jump to the next point we need to encounter while somehow adding all of the intermediate points that do not have part. So check somewhere if a point has its part. Okay, actually we have now some prefix here, and then we go furthermore here. We iterate over all of the points, and we say, okay, this partner is going to go here somewhere. Let's iterate this. This is inside. This is inside. Linearly iterating. When we encounter the next iteration here, we know that now we can implement this prefix and we can add +1 to the prefix. Yes. So this is n times n times n something like that. Okay, let's code this. Okay, so first we need to make a matrix of jumps. This matrix is going to be -1s, all the -1s. But how do we calculate this? Is we go for all of these here and we say li cal jumps, and now we are going to have like some calculation function here that actually what it does is just does that jumps at this point x and y is actually b, right? because we iterate over all of the x's, but we jump to b. Okay, so that's pretty straightforward. Now we have the jumps calculated. Another thing is we need to do is so first we check first what we need to do here. First we need to have some prefix, and then we go sweep line. And okay, so in the first step the prefix is 0. We encounter every one of, and then now we need like int jump is also 0. Then we encounter every one of them. So we go for I in n. And we say if jumps at I at s is not -1, jump is the maximum of jump and jumps at I at s. Okay, now that we iterate over this, we are going to say if jump is smaller or equal to s, we're gonna add the prefix yeah, like add the prefix and we're gonna plus the prefix. Okay, so now here this prefix sound like here something. So when it's 0, 0, I add all of these, right? Now the jump with rectangle 1. Yes, it becomes 1 prefix. Now, like, okay, jump becomes 1, and now becomes the jump is smaller or equal than S. Jump is the maximum of jumps from L to R, and S goes from 0 to M. That's correct. That seems correct. Oh, so okay. Another thing here. We need to check if yeah, so yeah, I mean how much time do we have left? 30 minutes. Let's see on this easy example here. What happens on this easy example? The points are like this. Now I iterate 1, 2. So I iterate C out L R. Here I iterate 0, 1. And I see that in this case the answer becomes 1. This is correct. 0, 2, the answer becomes 1 more. And this here, the answer suddenly becomes 5? How so? Yeah, so this is valid. this makes it so the jumps don't work if I go backwards. But there is one more edge case. And there is one more edge case. Is that I'm adding too much on the prefix. So I have to also take care of which was the last okay, so when the jumps makes it to here, I can add this one as well. Then the next jump, when I add it to here, the next jump upwards is either here or here. But if there is in the middle some jump, you need to go first. No. Like here, I don't like this. Jump left. We'll see. I don't like this. Just can create another array. And I'll say, okay, if otherwise, I'll just put them all on maximums. This should work the same way. Here jumps left. They're all int maximums, right? So if jumps left is smaller than L, so that's smaller than L. This should work. Like, here doesn't even check it. Oh yeah, so yeah, it's B. It's not A, it's B. Okay, but this is not correct. So I mean, what does it happen in this example? 17 minutes. What does it happen in this example? Oops. Okay. Let's say we have 3 by 3 now. We color red here, so red. We color green here, and then 1, 3 here. Then we color 0, 0 with here, with this one. And then we color 1, 3 with 3, 1. And then the same thing. Okay, and then okay, so the answer, let's pop up this window here. So the answer, the first answer from 0 to 1 says it's 6. It's already 6. There's like 1 here. There's 1 here. There are 2 here. And now here shouldn't be 6, should be 2. One, two, three. Okay, this is correct. This is correct. Now from 0 to 2. Don't overcount anything. So like it's 1. Oh, here this here is actually counted as here, right? Yes. So you cannot just overwrite. It has to be jumps left and jumps right. Has to be separate vectors in which like you store the maximum jump you need to do. You need to require. So okay, jump left and then jump right. So jump left is actually the minimum of jumps left A, B, and X. And then if it is okay, so this and this is int minimum. And then you need to have maximum here for the jump right, jump left, jump left, So this takes care of this, and now this takes care of jumps right actually here. This should not be 3 now, because jump right is more than this. And also we need to state that the jump on the other position on the left and on the right also is kind of worrying, right? It's like this doesn't make any sense. Jump right is maximum on the right and minimum on this. Oh, here should be A, not X. Now we are overkilling something. From this A, you can jump left. The left is from this X, you can jump left to A, right to A, and then this is X, and then I have only 10 minutes to come up with correct solution. Okay, so this is 0, and it's not 0, because like you can go further here, but actually here, like you could reset it. No, like I'm just going to upload the previous code. Just going to comment it out and upload the previous code. Just by what I'm going to do here is just going to say if all and then all will be just to get the extra case. The extra case is when Li is okay with like 0, 0, 0, 0. And if it is all, then the answer is n times n plus 1 times n plus, so I already have this, n times m. This is it, like yeah. It's what? It's 4 times 4, right? And then sometimes what is the answer here? It's, so this is n, this is m, let's say, and the answer is n minus 1 times n minus so makes yeah, it's like truths. It's like, okay, how many are chosen here? So n times n minus 1 over 2 plus n times n times minus 1 plus n times n minus 1 over something like so choose 2 points from here. And we choose 2 points from here. What's wrong? divided by 4. Is that the correct answer? Oh, why I got wrong answer here? Shouldn't be time limit exceeded on the first. How is time limit exceeded on the first? And they're all inside. Should be time limit exceeded. Is it due to this? Oh, did it finish? Oh, it finished. Wait. Where's the scoreboard? I mean, okay, like a lot of people saw this one. Like I don't know. Like I didn't have any clue how to. Okay, my camera died for some reason. Okay, so see you guys in the next video. My camera died, so I don't know.